Hi everybody. Earlier we saw how linked lists work, where they are a collection of nodes connected by pointers. In this video, we're going to go one level deeper and look at how the memory management side of linked lists work. Now, if you're in a high-level language like Python or JavaScript or Java, you will never have to deal with this. It's just trivial knowledge that you're going to have. And if you're using a low-level language like assembly or C, it's going to be critical. But independent of what language you're going to be writing your code in, it's just good to know more about how our data structures, especially popular ones like the linked list, happen to work under the covers. So let's get started. Now, before I go further, if you want to learn more about data structures and algorithms in a beginner-friendly yet comprehensive way, check out my best-selling book, Algorithms, Absolute Beginner's Guide, available in physical stores and in online bookstores. Links below, or you can go to Google and just search more for it. Now let's get to the star of this topic, which is memory management and linked lists. Now, when we looked at arrays, we saw that with arrays you have an index position that allows you to access an item directly by using that number. So for example, if I want to access the salami value, I know it's at index position 3, I just use that index position, I have salami directly. With linked lists, we don't have that convenience. That organization provided by index positions doesn't quite exist. So if I want to get to salami, for example, I have to start the beginning of my linked list, go through each item until I reach the salami node, and vice versa. If I had to go to find eggs or juice, same exact way. There's no concept of having direct access to an item inside a linked list. And so the two key landmarks we often have to keep in mind is the very first node and the very end of the node, which means where's the end of it going on. And the pointers make sure a chain of nodes is actively maintained. So you just hop from one node to another using the pointer as the bridge. And so any operation we do with a linked list, whether it's a deletion or an addition, all of it really requires us to take a node, modify its next pointer, and then make sure the relationship between the previous node and the next node is maintained. And that's really the bulk of what the singly linked list, which is probably the most common linked list design, tends to enforce. Now we look at memory. We've talked in the past that memory is in many ways never a clean slate. It's not a nice series of buckets that we can just slot things into. It's often messy. It's filled with various things all across the page. It's fragmented. Some part of our memory will be free, other parts will be taken up by our operating system and the applications when running on it. If you have something in your clipboard from copying and pasting things a lot, it'll be available there. Your tabs that you're using in your browser, all of them take up memory, and your memory regions will have all kinds of things to it. Now, for the most part, we don't have to worry too much about this. The operating system or the virtual machine tends to take care of these details for us, but it does help in getting a better feel for how data structures like linked list tend to work. So with the linked list, the way we operate is this. Let's say I want to store the values A, B, C, D, and E, each nodes that are subsequently connected by a pointer. When it comes to the way we store them in memory, a node gets slotted wherever there is free memory, and it just keeps going until it runs out of total memory. If there's a gap in the memory, there's like a region that is used by something else, not a big deal. We'll just skip that region and we'll go to the next available free space, because knowing how to go from one node to another is determined entirely by the pointer itself. So in this case, we have A, B, and C in one contiguous region. D is not available to be right next to it because something else is taking up that memory. So you slot D somewhere, we have a pointer from C to D that points directly to it, and then similar to E, there's a gap where some other item is taking up some memory. Node E gets there, and the pointer from D points to E to identify the next node. So in this case, you have a pointer from A to B, B to C, which is kind of implied, and then C to D is explicitly shown, and D to E is explicitly shown. And so this allows us to not worry too much about having the perfect ideal memory configuration. With arrays, we saw that each item in our array has to be in contiguous regions, has to be next door to each other, and if it's not, we keep finding somewhere in our memory a place where we have continuous free space to be able to slot our array into it. So if we're adding a lot of items to our linked list, again, it doesn't matter. Notice here that we've added beyond E, we added F, G, H, and I, and they're located all over the place, but it's totally okay. The pointer will point to the appropriate location and you're good to go, because at a high level, the linked list pointers refer to other nodes. Behind the scenes, they refer to memory addresses of the node. So if I go back to the previous example, for example, from H to I, it looks like a huge jump, visually, but realistically, it's just one memory address to another memory address. And that's what the pointer is ultimately referring to. If you'd like to learn more about linked lists, or you have questions about it, you want to discuss with other friendly community of other developers, go to the forum at forum.group.com for more details. And before we wrap this up, here are some quick actions you can take to go deeper on this particular topic, or to keep up with all the content that I regularly share. See you all next time.